All right, hello and welcome, lads and ladettes, to GLOBEBUSTERS Season 14, Episode 4. Today, Shane is going to do a presentation on the celestial and terrestrial sphere models. But before we get into that, we'll do a little introduction to the panel. Stone G, welcome, sir. How are you?
Good to be here. Thank you so much. I'm hatless, but I trust after a couple more days, the mail will take care of that since last night, right? You?
Yes. For those of you who don't know, we had a little trivia last night. ManofStone decimated. Liliana came in a close second. Shout out to Lily.
Yeah, she was pretty close, but not quite.
All right, then we have Shane down here. What are you up to, Shane?
What's up, everyone? Good to be back every week. It's going to be a fun press today.
Awesome. I'm looking forward to it. This series is one of my favorite. Like this, three-piece banger you have really ties everything together that you've been working on the last year and a half. So it's gonna be awesome. I'm glad that you're able to share it. It's gonna be fun. And I hear you added some new stuff from the last time you've done it. So we'll have some new info to go over. It's gonna be awesome.
Yep.
Fantastic. Cami, how are you?
I am doing good. I'm trying to figure out how, if you won the trivia, how did you lose your hat?
Oh, he hasn't got a hat yet.
It's that I won the hat as a result of winning trivia, and I'm waiting for the mailman to take care of things and deliver the hat unto me. Which in order to go, I should take about 8 months. So I'm really looking forward to that around Christmas or something. That'll be great.
The trophy hat where it says you're the best at trivia, right? Is that what the hat says, or it just says Ether?
Oh no, I've already printed one of those up. It's in the bag. Yeah.
Awesome, dude. All right. Well, Karen will be joining us shortly. So shout out to Karen. She is in transit to us. Shane, whenever you are ready to begin, sir, go ahead and give us a little introduction to the Prezi here, and we'll get going.
Great, cool. So yeah, this is going to be the two-sphere model of the cosmos, right? And it's two conceptual spheres. These aren't real spheres. There's just two imaginary conceptual spheres that actually, when thrown together, make up the globe model. And that's what we're going to be going over. The last time we did a prez, we did the geodetic datum, which embodies the terrestrial sphere. So we went over what is the terrestrial sphere. We're going to brief some that real quick before we continue. But for everyone here in the panel, if anyone has any questions, shout them out. If anyone has any questions in the chat, you can shout them out and feel free to stop me. But here we go. Right? So we're going to briefly sum up this last prez. What was a geodetic datum? Before we do that, though, we have the other celestial sphere over here, which I think most globers cannot distinguish from the graticule, the longitude-latitude grid. So before, I think this is a pretty good summary of what they've been doing so far. And they just kind of grab the model Earth, present the celestial sphere and the celestial coordinates. Job done. Off we go. All right, that's what the model's been showing so far.
Can I inject a theme for the audience to just keep in the back of their minds when we're going through this? And that is the concept of Euclidean space versus curved visual space that we see in the latter. We measure the former when we get out there and we get our rulers out and theodolites out and our everything out to measure what is where to where to where to where in terms of perspective. Everything changes because of the principles of curved visual space. And I think that's a really key element in how these transitions come to be. Go for it.
Yep, and we're going to be arguing later where the curvature comes from is actually, geodetic corrections over long distances and really infliction from the celestial sphere, because the real argument is we're going to be they created one sphere from the other sphere. They have two conceptual spheres, and one was created from the other, as we'll get into in detail. But again, the modern globe model here, as defined by WGS84, is the terrestrial sphere. Remember, we have the ellipsoid model, which they put forth, which is basically a datum, an abstract formula, an abstract coordinate system, which they tie to the surface of Earth very loosely using measuring meridian arcs, which we're going to go over that in a minute. But the basic principle is that these two things get put together, overlaid on top of each other to create the globe Earth, without which there is no globe Earth. The globe Earth model is really just these two component conceptual spheres overlaid onto another. And that's where they get celestial navigation. That's how mapping works. That's how all the things that people blame the globe for, the non-curving surface of the earth, they blame that for all these accomplishments. And it's because these two models are so nicely knitted together that no one can tell the difference, really. If we go back to how we defined a geodetic datum, like I said, it's an abstract coordinate system with a reference surface. So it has tied to sea level, and horizontal datums are what we use. That's latitude and longitude. That's how they tie that to the surface of the earth through this geodetic datum. And then we also have vertical datums, which are mainly tied to mean sea level and sea level elevations and such. So the terrestrial sphere, like we said, is the geodetic datum, and it is synonymous with its reference ellipsoid, which is the model that they put forth to represent it. These two things are identical, right? It's the same text. This is equally represented as this. This is the ellipsoidal model. And as we went over last time, it's at the backbone of almost every modern system where people blame the globe. Satellite geodesy, mapping and cartography, surveying and geospatial analysis, map projections, world maps, robotics and navigation, Google Earth, every time you get in a car, all the telescopes, it's all running off this terrestrial sphere model, the WGS84, which is an ellipsoid model that was assumed and put in forth, and then everything is internally consistent to it. But the only ever validation they do of this model is when they go to measure meridian arcs on the surface of the Earth, and they measure such a tiny amount that then they calculate the rest using astronomical latitude, as we showed before. And again, just a brief summary, we went over this book about the terrestrial sphere and how they were to deduce the figure of Earth from arcs, and that it is through the surveying where they use a collection of rods and chains, but they only actually measure a very small portion of the Earth using these rods and chains, and then they calculate the vast majority of it else, right? So if we did the percentages, it's less than 1% of what they're supposedly confirming gets actually measured. 99% is calculated.
It's calculated. I disagree with the verb. More precisely, I would use a verb like extrapolated. Y'all should look that one up. There's keen mathematical insight in that term applied here.
Yep, that's probably a more correct way to say it. Extrapolated from this tiny measurement, which they use servicing rods and chains. And they just plug it into this formula over here from their ellipsoidal model, and they go, boom, we have our new reference ellipsoid. Definitely measured the surface of the Earth to do it. And now we had this page before where we know that actually they say if you wanted to, get a real good meridian arc measurement, you want to measure 70 kilometers consistently. And none of these measurements extend more than 70 kilometers. In fact, they're only 1 to 2 kilometers in actual sequence. And then they set up these networks of towers that are interconnected, where they then judge the astronomical latitude between them and calculate the difference using astronomical latitude. So that's the summary of our terrestrial sphere model, how they use it for everything, how it's just an assumed ellipsoid, not a real sphere. It's a conceptual sphere. And the only time they went to confirm it was these tiny measurements of Earth that they went to calculate the vast majority of it.
Hashtag not a real sphere.
So they make 2 kilometers of ground measurement with whips and chains, and then they look at the stars and calculate the rest out.
Exactly that. Yeah, astronomical latitude, meaning deduce my latitude from the stars. So they do a little bit and they go, where's that star at? Where's it supposed to be? Boom, that's how long this arc is. Earth confirmed. Earth a sphere.
That easy.
I guess we shouldn't have been
extrapolated
surprised.
Indeed.
Yeah, how you can, so you measure 1 kilometer on the surface of the Earth, right, which is barely enough to tell a difference from a sphere and a plane anyway. And you're like, okay, look at the stars. Boom, measure that sphere. Measured it hard. So then the other part that we're just going to touch on briefly is how the terrestrial sphere applies to satellite and geodesy and astrogeodesy. Because recently our Globe Earth friends have put forth that, hey, ECEF measurements, which is a technical term for satellite data and how it's transmitted with the coordinate system in which it's represented, just Earth-centered, Earth-fixed, they say that proves curvature if you can extrapolate it and remove it from the model it's in. But we did touch on that actually the reference ellipsoid that we talked about is the basis for all of ECEF. In fact, when they define ECEF, they say that right over here is the surface of the reference ellipsoid, because they both have at their center the center of Earth's mass. So they say that actually, you have a question?
I was just going to marvel at this diagram here, and it reminds me of Idiocracy and every other geometric puzzle people have been forced to do as part of IQ tests. Does this not remind you all of trying to fit the square into the circle? just
Right?
mentioning it.
It's
Yeah.
exactly that. But then there's so like the Globers, the people who they try to argue these two are separate. But if you look up the definition of one, they literally can't define one without the other. The definition of this is both together. They use them
They're
interchangeably.
completely separate and independent. The fact that their z-axis is aligned for symmetrical transformations between the two means absolutely nothing.
Just a coincidence.
And this is how they do it. They say, look, well, the ECEF is the center point is relative to Earth's center of mass. And then the totally separate reference ellipsoid center point also is the center of Earth's mass. But look, they're totally not the same, and they're a different point. No, that's how they can overlay over each other, and that this provides the surface above the what, right? It's above the surface of the reference ellipsoid, not of any curved actual Earth.
Listen, I just have all these data points in empty space that when I happen to align it with this center of Earth mass, happens to describe positions on the ground. Coincidence.
Yeah, so like the using of astrogeodesy, or the stars to define positions on the ground, is how they arrived at creating a ground position for each celestial object, which is the backbone of celestial navigation. It's the intermingling of those two models, the celestial and the terrestrial spheres, when put together, work when you match the points like that. So that's exactly how they did it, right? And then, so this is another slide going over how you can't actually use ECEF to show curvature, because it'll only be showing the reference ellipsoid curvature with all the different basics. And we went through a bunch of ways on how that we could prove that, a bunch of testimonials, how it's always the reference ellipsoid. It's always in terms of the height above what? When you're defining height or a z coordinate within your ECEF, you're like, well, is it above zero? What's zero? And according to the definition we just looked at, it's the center of the mass of the Earth. But in reality, it's overlaid over the ellipsoid. So it's height above what? With respect to what? Is it the ground? No, it's the surface ellipsoid. It's always the height above the reference ellipsoid. So that's why covering the terrestrial sphere is important when we're talking about, this wouldn't work unless the surface of Earth was curving. I disagree. It would work fine, regardless of the shape of the Earth, because of the coordinate system in which it's refined and required. It has to work within these two datums. It has to work within the terrestrial sphere. It uses the orthometric height, which is the actual height of mean sea level, and it uses the geoid to convert it to the ellipsoidal height, and they use through the process of the deflection of the vertical, all which we went over last time, but we will definitely do a quick summary on those as well. Moving really quickly here, because again, this is the basis of the terrestrial sphere, but this is another way how we calculate ECEF in reference to the terrestrial sphere model, not the surface of Earth itself. This is the range measurement equation, and we can actually know that these terms right here, xi, yi, and zi, are literally directly dependent on the WGS84 model. So that when they say, we have a good globe Earth friend, Morty, who was pointing out where in this is it relying on the ellipsoid, and the answer to that is this term, and this term right here. Those are all directly dependent on WGS84. So again, tied to the ellipsoid center, which is WGS84, and then we incorporate a whole another model to make it more confusing called the geoid. And the geoid, of course, is the gravitational potential direction. Right? It's just supposed to be the model of gravity vector all over the Earth. And in here you see how it's applied to get sea level. It's the h equals h plus n, which is how they interpose the geoid and the ellipsoid on orthometric actual sea level heights, so that in fact they get mean sea level to equal curved, right? This is how level equals curved. They take level guides and they wrap them around their ellipsoid model via this surface reference of h. So the geoid over here is just defined as the only shape that needs a directional relationship to Earth's gravity field, right? It needs a perpendicular relationship to any point of direction of gravity, which is how you get this lumpy spherical thing that they show us all the time. What it's actually used for, though, is in deflections of the vertical, and how they, again, the other method of correcting or confirming our ellipsoid model, which we just straight assumed, is deflection of the vertical and meridian arc measurements. So we touch meridian arc measurements, they measure 1%, calculate the rest. The only other way they ever confirm that these reference ellipsoids are tied to the surface of the Earth is with this complicated process called the deflection of the vertical. or its proper term is the astrogeodetic deflection. In which case you align 3 of these vectors. You get your station over here, you try to get your deflection of the vertical, you pay 0 attention to the topographic surface, and you immediately pretend to use the geocentric latitude with the geodetic latitude and offset by the astronomic latitude. And then what you get is a difference measurement from vertical and measured in the east, west, and northwest directions to about this amount. And then they use these measurements to put an astronomical table so that when you use the stars later to navigate, they know the correction they have to apply to get you back to the point with which you're measuring. So that's how all that's connected. And this is a really big process of confirming the ellipsoid, because they're referencing using the geoid and the deflection of the vertical here to literally combine these 2 models.
Quick question. Okay, so the geocentric latitude is the reference of the position of the star on the first point of Aries, right? Like its zenith. The geodetic latitude would be that same position?
So that's like latitude, longitude, WGS84. That's where we're at.
And then astronomic latitude is just the position of the star at that time?
Yeah, like apparent position.
Gotcha. So, okay, so where it was apparent, and then the geodetic again, which one was that? That's
lat long. That's like that's the graticule essentially.
So that's where it's at with respect to lat long.
Yep.
Gotcha. Okay. All right. Thank you, good sir.
Yeah, this slide is like 4 different pages in that book put together so we can get the whole process, because they spend the whole time going over it. But this is really it, right? This is the end result. This is the setup. This is what they ignore. They throw in these 2 models to get these differences, and this is the overall picture of what they're doing, and here's the result.
So can we quantify that just for a sec? I want to take everybody's attention to the top left of this illustration. When we look at the astronomic coordinates and the geodetic coordinates, and when you take a look at that, what is that, psi that they're using? For the first variable, that's 40 degrees, 25 arc minutes, 36.28 arc second, 40, 25, 33.
Oh, yeah.
We're talking about 3 arc seconds. Those are 3/3600ths of a degree in difference. How is anybody with a plumb bob measuring that with any kind of accuracy? I can hear Bruce McGuire going in the background.
I'm doing it right now.
This is amazing levels of goofery, right? You know what I'm saying? When you actually plug in the numbers, the nonsense reveals itself immediately.
Dude, that's
this
so
is actually
funny.
taken from a real example, right? This isn't just arbitrary. This is from Station Yung Hall and some place that I pulled it from. Like I said, it's from an actual geodesy book, and these are their illustrations when they're teaching young lads how to do it. And this is the actual real example of the measurement they took from this station over here and these differences. So,
and lambda is half of that, 1.75 arc seconds of difference. Oh yeah, we're measuring that for sure.
That's so disgusting, man.
So that's how we know the Earth's a sphere, is that we assumed our ellipsoid model. We measured the deflection of the vertical. We measured our meridian arcs. We did 1%, calculated the rest of that bad boy, launched some satellites, bumped it on. Earth's a globe. Guys, what do you think?
Pretty much.
Well, I'm sold.
See, how else would you relate positions of the stars and time to positions of where they would be on the ground? Like, as much as they've done all this like weird backwards correcting that we're all going over now to like make their system work, it is a really interesting system to make a unified system where time equals angles to where the stars are, which equals where they're at on the ground. It's a really cool concept, but like look at what they had to do to actually make it work. It's like they're talking about subtracting arc like fractions of an arc second, dude.
Well, it got better over time, right? The very first deflections were way off because they did it in the south with a telescope in like the 1700s. And then there's a paper that we went over that's called The Use and Abuse of Vertical Deflections, which pretty much goes over how since it was since the inception, it's been used to hide the differences between these 2 models as a giant fudge layer and factor when taking measurements of geodesy all over the Earth. That's pretty much what it's for. That's what it's done. That's what the paper's all about. And that's what the dude says in black and white.
Classic, dude. And that goes in tandem with the old Arc of the Parallel books too.
Cami?
I'm going to dumb this down for like myself and a lot of the people because I thought it was really good, especially where you had it before and it's good going forward. Somebody in the chat last week was asking, what is a datum? and I don't know if you touch base, but doing it here again, datum is, you guys can let me too if I have this right, datum is going to be the singular for data. Data would be plural, datum would be singular, and so your datum is going to be a reference point. And I think it's interesting that, again, it's not, they don't call it a data set, which would really what it is a data set, but they don't let you see it as a data set. They only let you see it as a reference point as to where you are. So I think it's very, very interesting and sneaky that they have it. It's a datum, not a data set. That again, it works in what you're saying from a reference point. So when you see the word datum, think it's working from always a specific reference point. Now, is that correct, gentlemen, or?
Yeah, the way I think about it is a datum is what ties an abstract coordinate system to the surface of Earth. Without a datum, then latitude, longitude is just an abstract spherical coordinate with no reference to anything, with no meaning. Remember how we were talking about 0 point above the surface of the plane? A datum would be tying what the map is projecting to the actual surface and topography of Earth. But yeah, it is only singular, and they're only allowed to be used the provided datums, right? You got NAD 83, NAD 73, national. They would limit you to these spherical ellipsoid model datums only. There's no complement flat datum that you could just switch in if you wanted to, right? There's only ellipsoid model datums. There's only these coordinate systems. Yeah.
Further to your point, Cami, I'm appreciating that you're making it about now, and I think it's totally relevant. Arithmetically or mathematically speaking, you are not able to compute error margin with only a single data point. One datum. You see?
Mm-hmm.
It psychologically gears the user away from even thinking about computing an error margin, which is where these 2-3 arc seconds are going to come into play as soon as you involve a second interrelated data point. Indeed.
Yeah, we should have read the whole definition from the site that I brought up here. It just says it's an abstract coordinate system with a reference surface that serves to provide known locations to begin surveys and maps. And this way they act as starting points when you give someone directions. Like if you want to tell them how to get to your house, you give them a starting point that they know, like a building address or a crossroads. That's like that's a pretty good way to describe it, I think.
Your reference point, yes.
All right, any other questions before we move on to the celestial sphere?
Yes, from the chat, is the WGS84 the most updated datum?
It's definitely the most widely used one, but I think we did some history on it. So I think Clark Ellipsoid was the one they did way with the first, and then they did some evolutions, which that bloomed into NAD 73, which then bloomed into NAD 83, and then WGS 84 had its own history, and I think it's born of some sort of radio based survey. I forget the type of it. Someone will help me out if they know it. Yeah, I think I don't know if it's the most up to date. It's the one that's most widely used, and it's really at Google Earth when you open your phone. Since Apple Maps uses Google Maps, it's also when you open your iPhone. It's everything, right? It's the whole model of the terrestrial sphere, Google Earth. Like, so that, like, the other point is that's what we'd be fighting to replace. Like, our argument isn't that that's wrong. I'm not fighting to replace that. My argument is that the coordinate system is synonymous no matter the shape of the Earth because of the way that they've set it up and defined it. Because of its self-correcting nature, anything used within the coordinate system will adhere to the coordinate system, and they've done very little to tie that to the surface of the Earth. So then, why wouldn't both models be able to use this conceptual system, right? Like, I don't argue with any of it. That's my position anyway.
I see some thematic congruity here in that it is the WGS 84, as in, like you see at the top of this page, 1984. Go right ahead.
Yeah, that's definitely where it came from. That was the birth of it after satellite geodesy, of course, a certain amount. And it should be noted that after they started measuring meridian arcs, they just, as soon as the first satellite was made, they immediately repurposed all of them to survey the Earth in its spherical form. So satellite geodesy has taken a big part of this mapping since its inception, for sure. But we know that there's holes in that with the coordinate systems they have to use to make them reference a geocentric with Euler forces and centrifugal forces that can only be described if the universe was in motion around a central point. But, that's a different presentation. If we start talking about the celestial sphere, let's go right to the Wikipedia entry, and it says it's, an abstract sphere. So again, it's another conceptual model that has an arbitrarily large radius, which is mathematically infinite, and is concentric to the Earth. They say that all objects in the sky can be conceived as being projected upon the inner surface of this sphere, which is centered on the observer. If centered on the observer, half the sphere would resemble a hemispherical screen over the observer location. So all of this to say, it's only ever based off a hemisphere of observability, right? Everyone only ever sees a hemisphere, no matter where you are. And from this, they've created the mathematical model of the celestial sphere.
And this is where you should be starting to think in terms of curved visual space.
Right. So everything that we see is now bent around the observer. That's what they're describing. They're not saying that it's because of perspective and curved visual space. Their conclusion is, duh, Earth's a globe. But it's from the inside.
Yeah, they're saying that the light rays actually come in parallel, straight, and the only reason that they could deviate is because you're standing, on a ball, so you're the one that's tilted, creating this arc across the sky due to the contour of the Earth, and like that's a bold claim, If only there was a way to test that. If only we could draw triangles with celestial bodies.
These sun arcs here are the reason that they think the world is tilted, right? They're like, oh, well, actually the sun's going straight, and because light's all parallel, the whole world must be tilted over here, and that's why that we don't see it perfectly. That's literally like the birth of, perpendicular light rays and how they got the axial tilt and all that stuff. So again, the celestial sphere is an abstract concept, and it has an arbitrarily large radius, which is effectively infinite. And now, what's a sphere with a curvature rate that's infinite? What's a sphere that's curving infinitely? Oh, that's just a flat plane.
Oh, don't you get all mathematical on us, man.
Like, wait a second. That's indistinguishable from flat then. And in fact, if you think about it, the celestial sphere is a neat way to get the globers to utilize what is flat Earth baseline elevation angle measurements to stars. And then they just say that actually that's a tangent to a concentric infinite sphere, and that's how we can use the same angles. And that's how it works, literally.
Shout out to Tangies.
So what a trick. Celestial sphere is just, we're going to use flat Earth and pretend that it's a arbitrarily large, infinitely curving flat sphere.
This was one of the things that upset me a lot with flat Earth is I'd sent out holiday cards and thought I was so clever, being the atheist clever person I was, and they were a little thing on the front with axial tilt the whole bit, and it's like axial tilt, 'tis the reason for the season. So like I offended everybody all at one time. Now I even offend myself with it, but no longer do I believe axial tilt is the reason for the season.
Yep, the path of the sun is just, that's how we see it because of our limited view. But the way that I would describe the celestial sphere is I drew this little thing, and it's really just coordinate systems upon coordinate. So we got spherical, we got polar represented, we got hemispherical, we got some cylindrical with the inner plane here. And I just went coordinate system crazy and put some stars around it because that's how they're using it. They just put abstract coordinate systems everywhere. They describe it with spherical, hemispherical, cylindrical, Cartesian, coordinates all over the place, and it doesn't matter. But again, it's all based on this, right? Our view of the sky as a hemisphere, as we started with, as the celestial sphere is this defined on Wikipedia. This is how everyone sees the sky, right? It's the same for each model. So it's really model independent. So when we construct coordinate systems and models based on this hemisphere of observability, which is the same on either model, why would they then claim that actually this is exclusive to either model, right? Essentially, in the globe paradigm, anytime you reference a star or look up, that's a globe measurement. Anytime you look at the sun or reference the sun angle, that's another globe measurement. As a flat earther, you can't have any of that. That's their current position. But as we're saying, it looks it looks indistinguishable from within. We wouldn't be able to tell which model it is from the way it looks. So how would we not be able to use the same model? Right. So if we look through our old textbooks, this is how it's always represented from our good solar energy panel install guidebook. They say, hey, the sky dome is the visible hemisphere of the sky. That's how we want to position our radial solar panels to get the most energy. It's how they use the local celestial sphere. This is how it's always been depicted. You can do your zenith straight up the observer, and then you have this corresponding bend to the celestial objects as they go. Instruments are based on telling the angular separation. You get the quadrant, you get the sextant. It's all based on this half of view hemisphere of the celestial sphere, right? It's coordinate systems based on angles to the stars, because from this observation, they then construct spherical coordinate systems with the bottom. And again, just based on this, as you observe the sky, everyone sees this. And from that, they create the spherical hemisphere, the spherical southern hemisphere out of math. They use math and coordinate systems to explain positions of celestial objects, right? Here's a nice spherical way to represent it. Here's how you would spherically. Turns out, though, you can represent any number of different ways and you convert them in between with very little fuss, right? You can do cylindrical to spherical, and they're all part of Cartesian. But the main point is, what's the difference? What's the difference between, if we just have a hemisphere, what's the difference between representing it hemispherically and spherically? And the answer is almost nothing. The only difference between the two is this value. They have what's called a fundamental plane shoved beneath the two, which separates the spherical into northern southern hemispheres. And the southern hemisphere just represents when you don't see the star. So if it's circling in a circumference circle the same size above you, and this part is marked with it rising and setting, and this part is marked with it being beneath your feet, then the circumference is what gives it its predictive capability, and that these two models would become indistinguishable, which is where we're at. They represent them with the same sort of coordinates, and the only thing that happens is when you no longer see it, you represent it with a negative z value. We have questions so far?
Nope, crushing it. That's a big contention that we get a lot, is like, we no longer see the star and it's mapped to negative coordinates, therefore ball. And it's
Before it's beneath my feet, right? Look, it's beneath my feet for real.
It's like, yeah, the math would be the same. It's like, how do you represent something you can't see now? Oh yeah, it's just negative now. Like you like, it's not going to be a completely different thing, you know? So
Yep. They work identically. There literally is no difference mathematically, except this value goes negative for sphere. And if we're just going to keep it positive, then you can only describe it where you can see it, right? The ancient tool that did this alarmingly well was the astrolabe. It did a nice stereographic projection of the sphere onto a plane. It represented what is the celestial hemisphere onto a plane. That's what this tool is doing. That's what it's most famous for, right? If you look at where the zenith is and how it represents circles of latitude and in the observer's horizon, it's doing the exact same thing. And this was probably one of the first tools to do it. Yeah, so it does the projection of the celestial sphere over the local sky. So it takes what is your breakdown of your hemisphere, right? If you were to go in Stellarium, this is the azimuthal grid version. It just plops your altitude lines and horizons based on your visible sphere. And then from that, it overlays the celestial sphere, or another sphere, which has all the markings of the zodiacs and the stars and the positions. And when you spin this one on this one, you're matching the sidereal rotation of the sky to your local arc of horizon.
For those not familiar with the astrolabe, that's exactly what we're looking on the projection celestial sphere side. All the points that you're seeing there are actually the points in the sky where those stars exist at a particular time of day, a particular month of the year, et cetera, et cetera, et cetera. And the inner circle is a reflection of your quote-unquote latitude or distance away from the equator, and it would be closer to the center if your latitude were lower.
Yep, and that's the greatest example of what we're talking about. The way the astrolabe works, it takes all of the markings, right, where everything is in reality, and it puts it over your individual overlay, and then you just spin it to match what time it is, and then you'll get the actual representation of the celestial on your local sky. So we're talking about the two-sphere model, and we're combining the terrestrial and celestial spheres. And here, the celestial sphere, as our end result here, is that it's based on any hemisphere of your observable sky, taking celestial angles and measurements and then representing them spherically to get this conceptual celestial sphere. And if we go back to the beginning of so-called history and the beginning of the presentation and the beginning of our boy Ptolemy here, he is credited with first putting forth the two-sphere model in an ancient Greek book called Geographia that has been rediscovered and is easier to read than 17th century English books, as a matter of fact, but may or may not be his real takings, and is in fact just the first time anyone ever sees the two-sphere model. He's famous for putting forward both the two-sphere model of the system of latitude and longitude, and how you can use astronomical measurements to map geography. That's the other thing that he's really famous for. The book's also called Cosmography, which is the other name when you're combining geography and cosmology. So again, real quick about the book. It's the oldest book on cartography to have survived from classical period. It's one of the only things from like Eratosthenes period that is said to have survived, and it does.
The only thing that made it
Eratosthenes.
through history is
What
this
are the odds?
is this globe
wow.
model.
There's also critics that read it that say it sounds like it's been written by a bunch of different people, or that he had like a different splitting personality disorder, or they couldn't really figure it out. And it's like, oh, or it was a bunch of amalgamation thrown together retroactively to make us think, you know, either one of those scenarios are equally likely to me. But again, it's the oldest known book, and it's how it's hard to gather data and draw maps that champion the use of astronomical observation, meaning we're using the stars to map the Earth. That was the basic premise put forth, in which case you would need to understand and accept the two-sphere model of the cosmos, which is like right on page 1, figure 1 of Ptolemy's Geography as surviving from antiquity, says that you need to accept the two-sphere model of the cosmos to begin to understand, make it, and use maps. And they're doing this the same thing in modernity. They've taken that suggestion to heart, and as we saw when we broke down either model, they're going super hard on both of these models now. They have a hardcore developed terrestrial sphere and an equally developed celestial sphere, and using the overlay between the two, they have created the conceptual modern globe model, which is, you know, robust and effective. And again, just a little cast some shade on Ptolemy's Geographia a little bit. It's also got an enormous list of names, places, and every known location ever was marked with latitude and longitude before latitude and longitude was used or needed. And he used it in stadia, which is nice and vague, so everyone can pick your own definition of how long you think that is. So again, what he was using was the grid-based system, also known as the graticule. He invented mostly what is the first graticule, nicely enough, to be able to use maps, and then he's credited with a specific map projection. But the basic premise is that all of his data is based on astronomical observations, so latitude and longitude. He's marking the sky for for places on the surface of the Earth, and that all other science and geography is based on this actual book, because it says it's the father of geography. And actually, if you start to read it, right in the first couple of pages, he said, hey, I didn't make up any of this. I stole it from this guy called Marinus of Tyre. And he pretty much says that straight up. So we don't actually know who put forth all of this stuff. And Ptolemy said that he stole it from this other guy, and we don't really have much on Marinus of Tyre. But in this book, they also say Eratosthenes was also real, and Hipparchus was also real. And this is the only evidence of any of these three Greeks, is that each of the books backs the other up, but that we don't have them anymore. So make whatever sense you want of that. That's the historical record for Hipparchus, Eratosthenes, and Ptolemy based on the book Geographia. So then we go to, is it real? Is it real? Well, it says either you're not prepared for Ptolemy's fondness for suspension and resumption of argument, meaning that he just leaves things hanging and then comes back to them later. Maybe led to suspect that the text has been subjected to extensive interpolations, or even that Ptolemy did not know his own mind. Yeah, sure. Maybe he was just crazy and had multiple personalities. That's the
Just
basic
conceived
consensus.
of two different spheres based off of two different personalities, merged them together in a book based off of positions of the stars to find his position on the ground. I mean, I don't understand why you're questioning all this, Shane. It makes perfect sense.
So then all of his peers, of course, looked on him and said, yes, we should let him publish his findings for sure.
Published in 200 BC is withstood the test of time. The only one that was in that cave when they went to go find it after the fire. I think that's the story, but it says, so then this is the same book, and it says these apparent redundancies and inconsistencies, together with variations in the order and contents of geography, it is presented as the medieval manuscripts, has given rise to theories of the work's origin that deny its integrity. For example, hypothesizing that Ptolemy maybe wrote book 8, and then though the various parts were originally from separate compositions by other authors united in Middle Ages under Ptolemy's name. Oh. So you put together a bunch of spliced together parts that other people said, and then said, look, Ptolemy said. Okay, well, at least that's in there. Anyway, moving on. He's been famous for the first graticule and then his projection, right? His graticule of Ptolemy's second projection. He put forth this conical pseudo-conical projection. That's what it's famous for. That's what's on the cover of the book, is a little known map and his projection of the Earth in this type. Now, we're going to talk about the two-sphere model, but he also was known for this other two-sphere model. I don't want to get it confused. This is the Ptolemaic geocentric system and is based on epicycles, and it's describing, motion of the planets with retrograde motion, with bicycles, and all sorts of retrograde motion. That's not what we're talking about, but that is something you may find if you look into this. So that's his Ptolemaic system. That's not the two-sphere model we're talking about as it applies to geography, cartography, and cosmography, right? The two-sphere model of the cosmos, trying to map it out. Some other notable works from our boy Ptolemy, though, before we move on, is, of course, the planisphere, created from the planispherium, is another work by Ptolemy, which also gets translated as the flattening of the sphere. In case anyone was interested in picking up the planispherium, it's also where that would come from. And again, that's pretty much the juxtaposition of what we call globular space magic and flat Earth reality, or angles that have different angles to measurements to the stars and how they push everything to infinity to solve the problem that we have. But yeah, so another name for one of his works is called the flattening of the sphere. So we know where his head's at. Don't forget, the celestial sphere itself is defined as a conceptual sphere of infinite radius, which geometrically is the same and distinguishable from flat. So we've got a lot of flat Earth elevation angles being disguised and described with sphericity here, guys. So again, Ptolemy's two-sphere model integrated celestial and terrestrial coordinates to map the observable world using the graticule system. That's precisely what he did. So then we're left with what we have as a terrestrial coordinate system, also known as latitude and longitude, the coordinate system with which they use map projections. So latitude and longitude itself is not a map projection. It's what you call the infrastructure for map projections. It is the coordinate system that is being projected. When you have geographic and projected geometry and coordinate systems, we're dealing with projected coordinate systems over here with latitude and longitude, and then the geometry, the actual geometric coordinate systems, would be latitude and longitude itself. And its raw form and its conceptual form is spherical. It's a spherical coordinate system. Ptolemy used the same graticule model over here, except he predefined over 8,000 locations with his latitude and longitude grid using his unit of stadia. But the concept is exactly the same. We're still using the graticule today, and again, latitude and longitude is not a projection. It is.
Shane, does it ever go over how he went out and did those measurements? Because basically, you'd have to go out and take a zenith measurement on your reference night, and then compare it later. So was he was doing all this, or like what?
Well, so it doesn't tell you how he get it. If you read the book, as the summary was showing you, it tells you how weird it sounds like different people wrote it, and then the next section is just a chart of all the tables, numbers, and locations. Then it just goes on for pages and pages and pages and pages, and you're like, what the hell is this? It's very weird.
That's preposterous. Think about the hurdles that the Royal Society had to do the same thing, but the same thing, but independently. Confirming what Ptolemy put forward with his gratty. Dude, that's insane. This dude just whipped out 8,000 zenith measurements, dude.
To every known landmark, to every known city, to anything anyone's ever seen in his whole world. He had all the measurements in stadia. That's what that's what's in the book.
Dude. So oh my God, that's so crazy.
No, I know you only have 156 slides or whatever to get through. There was a previous slide, either one or two back, that was about Asia, and it not measuring correctly. And I was reading that right when we flipped it. So can we? Nope. Oh, crazy. No, it's forward from here. Hold on, right there.
That was it.
That was it. I just saw it where it popped in the black and yellow.
You guys saw it? Did I go past it again? I don't see what.
That's the third bullet point right there.
Oh. Right. So this is Ptolemy's graticule, where it was warping, and what they're talking about is the geometric extension of what this implies mathematically, right? Where which part of the world is stretched and which part would be not displayed correctly.
And Asia was an area that was probably stretched, it was saying, or
Yeah, well, it has a very. It doesn't even have all the countries, right? And they're certainly not. It's
Mhm.
his tiny area. So when he did this projection, they were speculating that this gets distorted. But the whole point of the graticule is that it doesn't. It's always only projecting the spherical coordinate system of latitude longitude as observed via the hemisphere. So it doesn't actually change. Each of the projections is showing the same data displayed differently. So whether it's skewed on one projection doesn't actually change the source, so to speak. Which is why Ptolemy's map doesn't really make sense. He had an incomplete coordinate system that he was, quote, projecting. He only knew where like a quarter of the world was, but he knew where everything in that quarter of the world was defined by stadia, and he could project that as a graticule. Like that's a weird concept. It seems made up.
Dude, it's super made up. That's so crazy. 8,000 measurements by himself, bro. Just like the observatories that they had to build, like to retell the story. This dude just had it all. That's it.
Yep, just knew him. Just knew him all.
Dude, they got us good. Well done. That's hella funny, dude. This dude just whipped out the whole world.
Geography was tough to get in English, but Eric helped me out, the librarian of Ether Cause, and once I had it, man, it was a good read. It was hilarious. All of a sudden, it just starts doing chapters of Laddie Long, and you're like, what am I looking at? What am I reading? What is all this list of giant data that you had? Anyway, so spherical, as the latitude and longitude is spherical, right? And then if we look through the modern definition, it is defined in modernity as angular separation on the graticule. It wasn't always that way, right? For the good old times, pre-1800s, latitude just meant breadth and width, and longitude was length or duration. But really recently, they changed it to mean the angular separation from the equator for latitude and longitude. And they say in the 16th to 17th century, and it so happens that was right after the graticule and right after we did the board of longitude in the 1700s. But we'll go into more of that during our next presentation.
And somehow, it took them 1,500 years to decide to make this step. Nothing in between. It was all Ptolemy from then, But now we're in the modern era, so we have to, we got to change it up. We got to give you some new lines to refer to.
Yep, this prez I'm mostly just putting forth what is the model and how we're going to use it. The next prez we're going to examine the timeline of how they say it happened and what we graduated from and how long we used each one. That'll definitely be worth looking into. Little suspect to say the least. So, and again, in modernity, we're defining latitude as on the graticule, right? It's measured in degrees, ranging from 0 to the equator. So they're literal parallels. They go from north to south, but they measure east to west, right? No, sorry, I said that backwards. Yeah, so north-south position. So they go this way, east to west, but we're measuring north-south. And then longitude on the graticule is they go the other way, but we're measuring east-west. Right? So they're used. The meridians and parallels is also what they call them, and they're literally defined as this within this spherical coordinate system. So now in the modern argument, when we say latitude and longitude, Globers are like, we got you, we win, that's a sphere. What they actually say is that's the globe, and that's not actually correct, right? That's the latitude, longitude, spherical coordinate system. That is what it is. But it doesn't mean that that's the surface of the Earth, as we went over with extensive detail. And again, our boy Ptolemy used all of his known locations to specify this in 1714. And then they had all these locations known, and that's how we're able to use latitude and longitude today, because thankfully we had his catalog. The basic argument that I'm putting forth is curvature as we know it, accounted for in maps, is only ever present in the celestial form, in this celestial sphere form, and in the conceptual terrestrial sphere. It's never actually measured on the surface of the Earth. The only thing that is measured is the flat level surface. When we go to measure our curved surface, they measure 1% and then calculate based off the curvature of the stars again. So then the position, of course, becomes, if latitude and longitude was reverse engineered from the sky, then the concept of a spherical Earth is just imposed on flat plane measurements through correction angles, specifically over long distances in astrogeodesy and geodetic surveying. So then the curvature of Earth is an actual illusion created by astronomic and geodetic measurements that artificially align the graticule to conform to our hemisphere of celestial observations. And so to confirm this, these two models are interchangeable now. For every point on this one, there is a reciprocal point on this one. So for our terrestrial latitude longitude grid, there's a point that matches our right ascension and declination of a star. And that's what we're going to go into next. That's how they got modern celestial navigation to work. It is the amalgamation of the two sphere model in practicality. They wouldn't work unless they could combine these two spheres to do exactly that. Let me see here. So we have our coordinate systems, again, our spherical coordinate system created from our hemisphere of observation. As again, pointing forth to the astrolabe, when you have your local horizon, which is your horizon coordinate system, and then on it you overlay the spherical grid, or where the true positions are, and you rotate them 15 degrees per hour, and that's how you get a true position on either model for a star. When we're talking about these two, though, there's a nature between each of these points that relates directly to this point. So we would define it like for every point on the Earth, specified by, say, theta, then there's a unique point in the sky. So that every point in the sky uniquely corresponds to a point on the surface of the Earth at any given moment, meaning that it rotates around the Earth. So it has to tie it to a point in the sky at a specific time. And of course, if we were to go through the process of working this out in our head, this is how you get a ground position. This is what produces a ground position for a star of its supposed zenith. They get the ground position of a star is when that geographic or subpoint is the actual point on Earth's surface where the star is directly overhead at that given instant. So then from those two things, we have mapped one from the other. We have taken the observable celestial sphere, right, which is our abstract concept with an infinite radius based on our hemisphere of observation, and we have constructed from it a one-for-one model, the terrestrial sphere, where every point is represented by this point. So that's why they have these represented conceptually and also consensually. Right? This one is around this one. They represent a concentric circle around this sphere because the points are so tied to each other. They only reference the equator. You'll notice the thing between these two that's identical is this red line, and that's the equator. Both of these are equator-focused and equator-centric systems, and that they can relate to each other via the celestial and terrestrial equators. But we're talking about how they contrive both of these models, and they can link them to each other via the ground position of a star. Using the ground position of a star, you can calculate latitude and longitude, which is the entire process and point of modern cell nav, is converting right ascension declination to latitude and longitude. You take an observation of a star at what time it is, and you do some math using the hour angle transformation, local sidereal time, Greenwich Mean Time. You do 15 degrees per hour to figure out where it was. You calculate it back to Greenwich Mean Time, and you get your position on the graticule. That's what's behind circles of equal altitude and all of the modern cell nav, the way you do it in the processes, is the two sphere model of the cosmos. So what's holding it together are these two conceptual models, which when put together equal the globe. If these two weren't created one for one from each other, the modern method of using one to get to the other wouldn't work. So the whole system is underpinning these two conceptual sphere models placed together. Now, again, in modernity, this is how they would say we use celestial navigation. There's an interesting point to be made as, was it always that way? When did we start to use the two sphere model? What are rhumb lines and compass roses? What's a wind rose network? When do we make the switch from, a Ptolemy chart navigation to the two sphere model? And that's what we'll be touching in our next presentation when we go over it. Next time I do a pres here will be the historical timeline of the two sphere model in maritime sailing and how they used it and how they didn't use it. But that's not for today. Today we're going to just finish up here with the terrestrial and celestial sphere amalgamation. So the best way to think about this in modernity is what they've done is if you just think about a star map, and this is just a Mercator map of the stars. You get the zodiacs here. If you look closely, you can see the path of the ecliptic, and you can see the zodiac, and you can see the normal progression of stars. Maybe it makes more sense if you look at it like this. But what right ascension and declination is really showing is if we were to rotate the stars over the flat Earth, these two models are one for one now. So we have the celestial sphere over the terrestrial sphere, and we have the celestial sphere rotating at 15 degrees per hour. So as you can see, each one of these points within a certain degree of latitude will never change its latitude. It'll never change where it is. It'll only change over what part of the Earth it appears at this moment, which is why the time is such an integral part when computing right ascension and declination over to latitude, longitude, because you don't know what star is going to be there unless you know what time it is. All of that is related to the first cross of Aries and the nautical almanac and what the true position would be. But what they've done now is if you can map the star field the same way you can map the terrestrial field, then what's the difference between the two? If one is mapped directly to the other and you can distort each one and you can map them exactly the same, then what's the difference? I think that if we look at star maps from before, if you look at what an AE projection of a typical star map would look like, you can see the stars splayed out as they rotate around the Earth. And again, think about it like this would be, as you see the Earth, the stars do their thing and they just rotate around them. Now, this doesn't represent the apparent position of stars, mind you. This is just the mapped geographic position. This is the ground position of all the stars in the sky mapped over their terrestrial counterparts. That's what this represents. If we were to take other maps of the star, like here's a constellation map, right, where it's just supposed to do the constellations and how it's typically portrayed as something like this, an orthographic globe. And you get the bottom. So again, it's concentric spheres here. This is a different type of projection that our concave friends like, where the poles converge at the top and the bottom, and they represent the graticule this way. No different from this representation, right? And again, we can use different star map. You can see the zodiac over here, and you can see the ecliptic. And once you outlay that, that's what it looks like over Earth. And here's a different representation. This is a azimuthal, I think, but representing the same picture over here. Here's the path of the sun. And you can see it with our concave map. So these two are similar, but distinct. This is the one we're going to be using when we compare them. Right, so this is how you would map a star field. This is how you would map a double hemisphere conceptual sphere. Right? If you could only ever see one hemisphere, then this is how you'd map the other one. And this is how it would look when you were finished with it. Right? Stars overlaid the flat Earth like that. Same sort of star mapping. Now, this is why the old school maps were all under the banner of cosmography. It was never geography and cosmology. They had them unified into cosmography because they understood you couldn't tell positions on an Earth that was mostly water without referencing the stars, the only thing everyone could see from everywhere. So all of their models were wrapped up in the notion of cosmography, where of course you wouldn't separate geography and cosmology. You couldn't do it. In the modern heliocentric model, cosmology represents something so big and abstract, and science, like you get quantum mechanics and time holes and wormholes, time travel, all sorts of nonsense is wrapped up in there. But if you bring it back to the geocentric flat Earth perspective, where all of cosmology is the Earth, we're the basement of the world, then of course all of the stars would be wrapped up in our representation of geography. So of course cosmography makes way more sense to us than it does to them. And real quick, I got some old school star maps here. If you ever looked at them, now you can see that you can look at the type of projection you're looking at. How they choose to represent the stars is very similar to how some people choose to represent the Earth. If you look at this double sphere hemisphere projection, it looks very similar to me about the southern sky would resemble the northern sky and how you choose to represent them on a map. In fact, if you put them side by side, you might see some similarities. You got some zodiac projections over here, a nice star map with an azimuthal equidistant, the actual projection of the orthographic globe with side to side, and then the convex terrestrial sphere map as we saw prevalently through the 1700s. Again, back to the star map, looking at how the zodiac would be mapped. I like the ones that have just the zodiac symbols as they map them because you can't even tell the difference there. They look exactly like the terrestrial sphere maps that we had before. And again, you can have a concave Earth showing that, oh, actually, this is because the Earth is concave. No, it's just the type of star projection that people like to use during that time. The one thing that is weird, though, is that when you look up maps on Wikipedia, from 1700 to 1799, these are everywhere and then nowhere again. And I don't know why they say that is. All of a sudden, they were great, and then all of a sudden, nobody used them anymore. If we talk about the first cusp of Aries, right, that if we look at what that means, that's really just a point in the sky, which is relative to the location where it is on the March equinox, and it serves as a 0 point for the coordinate system that we're talking about. So it's just like an epoch or a reference point, and it's currently located near Pisces, but it has nothing to do with what we're talking about. That's just what we're talking about when we reference for the celestial theodolite. When a star has a true position, it's relative to this marking. So where it was at equinox, and then they march it around 15 degrees per hour. What we're talking about is this then, right? They take the the actual equinox, and they just march it around. So the first couple of Aries is over here. This is what this is right here. Aries is over here, and we're talking about stars' other position relative to that time, and that's all it is. So is this specific to the globe? Does the globe own all observations of the sky, or can you equally just distort what you see from your hemispherical view into a contrived spherical coordinate system and then spread that graticule out flat over each other like this? To me, they are identical. There's no distinction between the two here. So that's why cosmography is the combination of the celestial and terrestrial spheres, as you were to put it. So again, the celestial sphere being represented by the hemisphere that you observe, and then using math to have an abstract coordinate system to represent it spherically. Our terrestrial sphere being represented by the geodetic datum, our WGS84, our ellipsoid model that we created and assumed from nothing, and then verified with meridian arcs and astrogeodetic deflection. So those are the two put forth, and together, the modern representation of that is the modern AE map. This is the modern cosmography, right? It's not separate reference of the latitude, longitude. You can't separate that in modernity from the maps. So all the maps that we know of and use today are really just the celestial and terrestrial sphere models put together. It is the conceptual, celestial, and terrestrial spheres put together. That's really where we're at. So that's what I got. About an hour. There we go. Not bad.
Made in the shade.
Nice.
Fantastic Prezi, sir.
Mm-hmm.
Questions? How we all got stuck into, absorbed into the two-sphere model?
Now, I know that you say it's next week that we're doing history, but where did you find the oldest place? Because I have where I found the oldest. We could have a contest on that, maybe a trivia contest. But where was your oldest markings of it getting switched to a sphere?
Oldest what?
You were talking about the history of it being a celestial sphere on the mapping and on the different things, or where in history it got switched to that globe model.
Right
Yeah.
back to Ptolemy. It's day one.
Yeah, so the important switch port, without giving too much away, is right about 17th century, the foundation of the turning of the century with the Mercator map. And that was supposedly the thing that made, the sphere possible, and everything was hunky-dory, and everyone can use the two-sphere model with their Gerardus Mercator projection of like 1690 something, I think. But we'll look into that for sure.
Yeah. One of the fun things going back in history, taking it all the way back, don't know if this will be of interest or not, but in the Odyssey, I think it was the Odyssey. In the Odyssey, when you had the War of the Titans, you know how Atlas is always pictured holding a globe up? And holding up, the sky, the globe?
On his shoulders. On his
On
back.
his shoulders, yes.
Way up top.
You'll know that, like, in that time, it was definitely a flat Earth. So if you go back to the original story of the War of the Titans, Atlas was on the losing side of the War of the Titans, and his penance is to hold up the sky for eternity. And so he was sent to the westernmost tip. So I was looking at your map too on your things that were eastern and westernmost. He was sent to the westernmost tip of the land and sent to hold the pillars up for eternity because they fucking broke the sky during the War of the Titans. So then they had of course, Hercules built the pillars. There's a whole story of that getting up and that, and it took over the whole thing. And so you have the pillars going up and the different things happening on the westernmost tip, and he was free. But then what happened were the gods actually redesigned the skies, so we would not be able to figure out the skies again. So at that point, the gods that were on the winning side, when the sky was broken and when Atlas was told to hold the edge of the skies were all redesigned. And so I think the oldest thing I've heard about the skies and them being redesigned is in the Odyssey and in the Iliad. Just thought it was a fun story because the way that we nicely took it into a globe and always show him holding a spear on his head when, again, that was very much, he was on the westernmost tip of the land. And how can you be on the westernmost tip of the land on a sphere?
Classic
Think a lot of-
reinterpreting history to make it match the current asserted paradigm. See it all the time.
Yep.
I think you're going to find that a lot too on all the mappings when you're doing that. A lot of your names, not when you're doing that they redesigned it onto the globe, but we always had the western and the eastern tips. I mean, there's always been Asia means east, Australia means east, Anatolia means Near East, and you have the Middle East. You have all of these things that are of the east, and you'll have of the west in that. But we named all of these things before we put the globe on there, and then we had to. Why would you have east and west on a circle, and how would that get into that? So that will get into fun stuff too. I think when you're looking at doing the maps.
Yeah,
Is
the
looking at it differently from east and west instead of in a circle.
well, it's all representing the same spherical coordinate system, right? Which they derive from the hemisphere of the sky. That's what I keep trying to bring it back to. Everyone sees the same hemisphere no matter what, and they just constructed a comprehensive model where they pretend things are beneath your feet when you don't see them. They represent it with math correctly. They get the correct prediction for when it comes back around, and everyone accepted it. No one looked back.
It was actually very, very, very well done.
Yeah. Yeah, awesome Prezi, man. I like the
nice.
first cusp of Aries slides that you added. That's such an important concept in relating positions of the stars to the ground and how they did everything. It's a really pivotal concept to understand because everything is based off of that snapshot and then adding 15 degrees per hour to it so that they could relate angles to time.
Yeah, I was trying to get a visual that would show that's not exclusive to anything, right? Like if we start with that one, this one, like yeah, like the stars rotating around the Earth, everyone cool, everyone agreed, no one's fighting this, and then we bring it like okay, well then we're just gonna represent.
I think another
right?
key aspect to remember too is like it's not just that because we're looking at a complete product where we have all the placements and then now we're rotating it in unison at 15 degrees per hour. But each one of these positions of the stars to be put on here was observed by a single observer taking a zenith measurement at a specific time. So these are all stitched together to provide this topographical view that we're like looking at as like a whole system, outside of it. But it's really just derived from we just based off of what one observer saw at a particular time.
Yep, and we talk about it all the time because we're trying to reference what a true position is, and all that is someone decided a 0 point, an epoch, a reference. They call it the first point of Aries. That's all it is, and then they just measure everything else in accordance with that, so that everyone can make the same measurements. That's all it's in reference to. It's not heliocentric exclusive. Doesn't mean the globe model's right. Doesn't mean the globe model owns observations of the stars. It's just that's where we're referencing it.
I think they might have done that because of seasons, because Aries is March. That's why it's considered the first sign, because it's like when springtime, it's like when life starts coming back.
Oh, absolutely.
I think that's why they started Aries.
For sure. But yeah, they just need that snapshot, and then that's their comparison point. So everything off of that is
Makes thematic sense. Yeah.
Yep.
Right. Well, back in the day, a lot of stuff would have depended on like the harvest and stuff like that, where most people probably don't think about that in modern times.
Yeah, the whole life was built around the harvest. The calendar was built around the harvest. Lunisolar calendars, they were changing how they told time. Everything was built around that. Yeah.
Yeah.
While you were going over the Prezi, I was thinking about all the times I've seen the globe, thought about the globe, and never realized that it was just the positions of the stars that make the globe. Like that's what it really was the whole time. It's always like, you see a globe and you're like, oh yeah, the ground's ball, not the sky's a ball.
Well, dude, this has been coming together for a while, right? The two-sphere model is how they represent it. It's how they gut us too, and it's just based on mutual. Like we can both observe the hemisphere of stars. That doesn't mean it's exclusive, except they made it exclusive and everyone bought it. That's every time you look up, that's a globe proof, dude.
Yeah, you can only argue exclusivity rhetorically. If you introduce another variable like a terrestrial intersection, it's over.
Yep.
Yeah.
Next time we'll go into this stuff, rum lines and how they use it.
Any other questions from the audience down there on YouTube?
Didn't see too many questions. Oh, there's a question from Titus here. He says, Shane, I have a question. Can you point me to the best channel to explain the Paris clock? I kind of understand it.
Prague?
Clock? I think he meant Prague, but he's spelled a different word. There's no Prague in there, but I assume that was Prague. But yeah, you're Prague clock Prague clock master connoisseur, aren't you?
No, but I got a slide that shows all the components and what each function is somewhere for sure.
Oh, there's a bunch of videos on YouTube explaining how to read the Prague clock and what it all means.
Yeah, I know that it has detail that you can use to predict eclipses. So it tells you like the moon's position, the phase of the moon, the period of the moon, its synodic month, where it was in its where it is in relation to the sun, its perigee, its apogee, like everything that you need to predict eclipses you can get from that clock, which is amazing.
That's awesome. Yeah, I think that was it for questions. Yeah, fantastic Prezi, man.
Thank you guys.
Next week will be a ManofStone classic. Be something from Stone's channel. And then as we wrap up,
I wonder what it's going to be.
Dude, I can't wait. I can't wait. I'm excited. All right. So, Karen, what do you got coming up on this coming week here?
I've got coffee talk tomorrow morning. That's about it. Maybe Thursday GLOBEBUSTERS with Cami.
Awesome. Cami, what do you got coming up?
Oh, I have a lot of the same. Now, Stone, if we miss Sunday's GLOBEBUSTERS, it's not because you're presenting. No. No, we may be in Nashville next week and we may not be in there, but I'm teasing you on it.
Well, that's cool. No, do what you got to do, man. Hey, that's the best part about streams. You can just come back next week and it's still sitting right there for you to watch.
Although I have to say, I've been digging the more the merrier GLOBEBUSTERS methodology this season. I think I like having more people here. This is great.
It's awesome.
I was starting to feel there when you had us all stacked on the right side, I guess the right side of the screen there. A little bit like we're watching the Brady Bunch. Like I could reach up and get something from Alan and then toss it down and give it to Shane. And I could look down and say, hey, what's going on down
We should definitely do a bit with that.
I was going to say, I kind of want to do it now.
Oh, man. Now I'm thinking of different scenarios. Okay.
Yep.
Stone, what do you got coming up this week, sir?
Oh, whole lot of private stuff can't tell anybody about yet. But again, like I said last week, it's not going to take a week, but I'm working on a video or two. And you will know when they come out, that's for sure.
Fantastic.
And it's private. Why is it secret?
Well, he keeps them secret until he reveals them. He's a, like a magician or whatever.
It's all part of showmanship, isn't it, gang? Come
yes,
on.
that's the word. Yeah, magicians are showmanship
stuff that we lack. Yeah.
Yes. Whereas we tell everyone immediately what we're doing, show them in real time. Classic. All right. So to wrap us up here, coming up for Monday, we have a celestial theodolite update on Ether Cause. So that'll be on my channel. We'll be over on the Earth Awakenings Discord. If you guys want to be participants in that, you can find us there at 8 p.m. Eastern. And then Tuesday will be Ether Roundtable number 96, where Shane will be presenting on, is Stellarium safe to use, or does it mutually exclusive belong to the globe always and forever? And can we never can we never touch it, speak of it? Should we shy away from it? Anyway, so he'll be going over that.
And will it infect your soul?
Yes. Is it the source of all things globularity? We'll be touching on that. And then I think we're good for the week. If anything else pops up, check the YouTube schedule.
Nice.